Thanks also to the organizers for putting together this really interesting workshop. So we have all learned or heard a lot about altermagnets in this conference and the role that symmetries play in the different order parameters. I guess the point of this, my first slide is just to acknowledge the very inspiring original work and to give away how I think about the symmetries in these magnets. Basically, the goal for my talk is very simple. I just want to tell you about this work we did together. This was with Ron Birol from Minnesota. Van Wildo is in Brazil, in Goiânia. And this guy, we have seen pictures of him where he was slightly younger. I just wanted to show you how he looked like when you first met back in Brazil. And in this work, we were coming from the problem of trying to understand multipolar orders, especially octopolar orders in itinerant electron systems. And at some point, Raphael pointed out to us that this has connections with altermagnets, so I tried to understand that. And these were the main questions that we were interested in. If you start from some Hamiltonian for some altermagnet and take into account the crystalline environment, by which I mean the spin-orbit coupling at some level that will break the spin rotational symmetry from the SU2 down to a discrete point group symmetry, how much of that picture survives. And also, if you have an external magnetic field or some other parameter that in principle can perturb the altermagnet, how much of that survives? And can we drive phase transitions and of what nature by varying the magnetic field? So at first, we were thinking about altermagnets in terms of band degeneracies for spin up and spin down. So at first sight, it looks like if you apply a magnetic field, you're immediately going to split the bands. It's going to look very much like a ferromagnetic band structure. But the story here is that I want to tell you is that actually depending on the field directions and what symmetries you preserve, it's actually possible to have a transition at a finite strength of the magnetic field. And this transition has some topological character. Okay, so we're going to consider only metallic altermagnets and work with a low energy model. By low energy here, I mean they're going to assume that you have some low filling and the bottom of the band is near the gamma point and going to expand for a small momentum near the gamma point. So as you know, the altermagnets have the sublattice degree of freedom, but we're just going to keep this lower band, and then we're just going to write down some 2x2 matrices represent our Hamiltonians, and we're going to be guided by symmetries. So for the dispersion, I'm going to take the usual quadratic dispersion. And then here, this part will come from the interactions from the symmetry breaking with some order parameter here that I'm calling phi. Lambda here would be something proportional to the interaction strength. And this order parameter in general, depending on the point group, you can have representations with dimension higher than 1. That's why my D vector here has this extra index I here. And then guided by symmetries, you're going to consider that the order parameter breaks time reversal symmetry, but we're going to focus on the case where you have inversion symmetry, so we can rule out linear in momentum terms like spin orbit coupling, and then going to assume that there is no ferromagnetic moment, what we call the pure altermagnet, either because of symmetry constraints or just because it happens to be very small and negligible. Yeah, so we went through this exercise just in the spirit of showing tables. We went through this exercise of going through these point groups and writing down the symmetry allowed terms. Given these constraints that I was talking about, we want the order, the parameter phi to be odd under time reversal. Then this D vector here has to be an even function of momentum. If you rule out an S-wave component, then this even powers of momentum, we start a quadratic order. So these are the Hamiltonians that we're going to look at. Actually, of course, I'm not going to go through the entire table. I'm mainly going to focus on this example where we have a one-dimensional representation in the tetragonal symmetry, this B1G minus stands for the odd time reversal, odd under time reversal. I should point out that, just to go back to this table, that here you see that there, in addition to the momenta, the components of the momentum, you have some parameters etas, eta 1 and eta 2. Whenever that shows up, it just means that the coupling constants for those different components in the Hamiltonian are not constrained by symmetry. So the details here are what these parameters would be. Well, of course, will depend on the specific material. So in this case, for example, of this representation, you only have one free parameter eta. If you want to recover the collinear case in this way that we wrote down this D vector, that would correspond to taking eta to be very large and neglecting the other two components. But in general, if you're just being guided by the point group symmetry, all three components are allowed. And in this case, the D vector has all three components. This means that the magnetization is also going to be to have all three components. So that was the first conclusion, that if you have this general crystalline environment in 3 dimensions, the magnetic state is not going to be collinear. So we wanted to think about some examples where this could happen. And then, so here's one that we discussed. So if you think about the perovskite structures, where usually you start with this structure, and if you have magnetic order on the B side, antiferromagnetic order. But in many cases, it happens that the oxygen octahedron will have to rotate to accommodate the atom in the A site. And when that happens, you lower the symmetry, you have to double the unit cell, and then you basically turn your antiferromagnetic material to an altermagnet. And then we wanted to see how this happens. So Turan did some ab initio calculations. And for this example, where the manganites, like this one, where the magnetic order is of this type, with different ordering wave vectors along A, B, and C directions, which are represented, the different components are represented here separately with different colors. But if you add up all three components, in general, the total magnetization here will change direction in real space, so this state is not going to be collinear.
Yeah, but most of the magnetization is along
the C-axis in this case, right? So it's C-type.
Oh,
no, I don't know if it's the C-axis, but it's B-axis in this case.
The A is G, so it's a pi, pi, pi.
Calcium, the pure calcium, okay, yeah.
Oops. Yeah, so this was in real space. It also had some, of course, consequences in the band structure in momentum space. And then we wanted to look at our simple effective Hamiltonians in this low energy model. So, and in general, if you write that kind of Hamiltonian, you can diagonalize it this way. This H of K here will be my 2x2 matrix that has this simple dispersion. And as you know, you're going to get degeneracies whenever this D vector here vanishes in the BRID1 zone. Right? So the question is, when does this happen if you have all three components of the D vector in this in the case of discrete spin rotational symmetry? For this example that I'm focusing on, the B1G minus representation, if you only had, say, the Z component here, then you'd have nodal planes where the D vector vanishes, and then the state would be collinear, and the polarization would switch as you cross the plane. But if you have all three components, then the condition is that for this to vanish, you have to take the intersection of these three planes, and this will happen along these nodal lines that lie in the X, Y, and Z axis. So the picture is like this. If you have a metallic altermagnet, you can draw the Fermi surfaces by the condition that this dispersion relation will be fixed at some Fermi level. And then what will happen is that you get the band degeneracies where this Fermi sphere with the proper Fermi momentum touches the nodal, is crossed by the nodal lines. We call this pinch points because it's really where these two surfaces will touch, and this will happen at these points along these high symmetry directions, and then yeah. So for this example, for the B1G- case, in general you would have all three components, but here you can look, for example, at the spin polarization along some high symmetry plane. So take, for example, the KZ = 0 plane, where three of these components vanish. Here I'm representing the Z component of the spin polarization in these colors as a function of momentum over these Fermi surfaces, just to illustrate that if you take the KZ = 0 plane, then you only get red and blue, which means the collinear states, in this case the D vector points along the Z axis. But if you go out of this plane, and in particular go around this nodal line, then the spin polarization will rotate, right? And then this, and it rotates in these different ways with the spin polarizations of the two, these inner and outer Fermi surfaces that only touch at these pinch points. We wanted to look at this in more detail, so we try to simplify the Hamiltonian a little bit more. So we looked at what happens if you take this effective Hamiltonian and expand it in the vicinity of these pinch points. So take, for example, this one along the kx axis at some finite Fermi momentum kf, and expand it around with some small parameter q. And then the Hamiltonian that comes out looks like this. So if you take a cut at constant qx, say qx = 0, which is the plane perpendicular to the nodal line right at this pinch point, then this looks very much like a 2D Dirac Hamiltonian. Whenever this parameter eta is non-zero, you actually get these two components. And from here, it's even easier to see that you get some Berry curvature. And if you define some Berry phase by winding around the nodal line, you get some non-trivial result, which is exactly what you get from Dirac point in 2 dimensions. And actually, if you consider the whole momentum dependence in 3 dimensions, this Hamiltonian is not just this Dirac part. You also get this term which is proportional to the identity. And this is very much like what you get from this type 2 Weyl semimetals. It's a different context, but it looks very much like the same. But in that case, it also happens that you have 2 bands that touch at one point. But you get a finite density of states because you tilt the Dirac cones. And to emphasize this analogy, we just plot this the energy here, the dispersion, as a function of momentum ky and kz in the directions perpendicular to this nodal line. Right, so you can see that it looks like a tilted Dirac cone. And then the question is, if you start perturbing this Hamiltonian with whatever kind of terms that you want to consider, how much of this will survive, and can you drive some phase transitions? So we want to characterize this phase in the more generic case in terms of this momentum dependence spin splitting. We're going to say you have this altermagnetic phase. Whenever somewhere in the grid-1 zone, you have this spin splitting vanishing along these lines that are dictated by symmetry. And in general, if you impose that this D vector has to vanish, that will give you, in general, has all 3 components. This will give you 3 nonlinear equations for this, the components of K that you have to solve. And it's not obvious that this will have some solutions, but we can approach the question this way. You think that what matters here for this question of this spin splitting is this interacting part of the Hamiltonian that contains this altermagnetic order parameter. And the question is, if this thing, this Hamiltonian has zeros in the Brillouin zone, and whether if you're allowed to perturb this, you actually get a stable gapless spectrum. So this problem had already been studied in the context of gapless topological phases. There, what matters is if you have some dimension for your real space, you talk about the codimension of your Fermi surface in the generalized way. So you can have, for instance, Dirac points in 2 dimensions. The closest analogy with what we're talking about would be like this nodal line semimetals, where the codimension of this Fermi surface, which are nodal lines, is this parameter p equals 2. So basically, we took advantage of the classification that already had been done and tried to find where our Hamiltonians are in this table. So basically, go through all cases that in the table I showed you before for these low energy models. They all fall in the same class if you consider only non-spatial symmetries, by which I mean charge conjugation, time reversal, and chiral symmetry. And then in this case, for codimension p equals 2 in 3 dimensions, that's our nodal line, and we're in class C because our Hamiltonian doesn't have time reversal symmetry, but it has charge conjugation as this anti-unitary transformation that acts like this in our interacting part of the Hamiltonian. So in this case, you look at this table here, there's only a big 0 there that tells you that there's nothing topologically non-trivial if those are the only symmetries that you have. However, we go back to the Hamiltonians we had studied, and then you realize that in all cases, these nodal lines, they lie on some mirror planes. So we have this additional symmetry, and of course you add more, as usual, you add more symmetry, the tables only get bigger. This is perhaps too small to see, but I just want to highlight that in this case, for the cases that we're interested in, we have reflection symmetry here, which is written as in terms of Pauli matrices. So this will be the component of the Pauli matrix in the direction perpendicular to one of these mirror planes. So it acts on this this Hamiltonian like this. And it's also important that this reflection operator anti-commutes with the C operator, the charge conjugation that I defined before. So in this case, all the Hamiltonians that we wrote down, it's possible that, it's also important that the nodal lines do not fall on high symmetry directions. I'm going to show that in a minute as for some examples. And in that case, you do get the possibility of having something which is topologically non-trivial, and the topological invariant in this case will be associated with the eigenvalues of these mirror symmetries. Okay, so we consider one particular kind of perturbation. So we're going to add this Zeeman term with this magnetic field. So, and if you combine this with the Hamiltonian that I showed you before, this is essentially equivalent to shifting the D vector in this way and asking whether this new transformed D vector will have zeros somewhere in the Brillouin zone. So going back to my main example here, let's take this D vector for the B1G minus. And then in this case, we have the nodal lines running along the Kx, Ky, and Kz axis. But if I apply a magnetic field along the Z direction, then in this case, we preserve the mirror plane in the XY plane. The nodal lines that run along Kx and Ky can be protected by this mirror symmetry. And then in this case, as I told you before, for Kx and Ky equals 0, then the Hamiltonian will reduce just to something proportional to sigma z. That's the collinear state. And you can label these different regions in the plane by the eigenvalues of sigma z, which are at the same time the spin polarization and the eigenvalue of this mirror symmetry, right? So in this case, you can define the topological invariant as just being the difference in the eigenvalues for a given band as you cross the nodal line. And this was the original, this is what the spectrum, or the nodal lines look like in the absence of this magnetic field. If you turn on the field, then what happens is you break this the tetragonal symmetry, and the nodal lines are now determined by this equation. So basically they become hyperbolas in the xy plane, and controlled by this H parameter, essentially the ratio between the magnetic field and something proportional to the order parameter of the altermagnet. And if you keep increasing the magnetic field, what happens is that basically you pull away these hyperbolas. The pinch points correspond to the points where these hyperbolas cross the sphere with a fixed Fermi momentum. That's where the true Fermi surfaces will touch. Eventually, if you keep increasing the magnetic field, at some point the hyperbolas will go out of your sphere. This defines one value of this critical magnetic field that will depend not only on the altermagnetic order parameter, but also on of course, the Kf, the Fermi momentum, the size of your sphere here. So, and this is what it looks like in 3 dimensions. If starting here at 0 magnetic field, we have, I'm not showing the nodal lines here, but they lie along the axis as before, and then these 2 Fermi surfaces will touch at these pinch points along the axis. This is just, here it's just a projection in the Kx, Ky plane, which is perhaps easier to see the projections of the Fermi surfaces in that plane. And then if you turn on the magnetic field, what happens is that these pinch points will move in some directions. For small magnetic fields, they're still there, but as you keep increasing age, they will move until some point where they meet. And then for higher magnetic fields, basically they're gone, and you fully split the 2 Fermi surfaces. The degeneracy points are completely gone now. So that was in our low energy model, where I'm taking just this continuum limit dispersion, but something similar can also happen on the lattice, and in that case it doesn't even depend on the transition doesn't really. There is one, let me say it this way, there is one critical magnetic field that does not even depend on the size of the Kf, because basically at some point these nodal lines will be completely gone. In the low energy model, they were hyperbolas. If you just translate this model to the lattice, say to the square lattice now, what happens is something like this. You just replace the Kx by sine of Kx and so on. And then you turn on the magnetic field, the nodal lines that were along these high symmetry directions will become closed loops. And the area defined by these loops decreases as you increase the magnetic field, until at some point they basically shrink to 0, and that's the critical value of the magnetic field, where you just get non-zero spin splitting everywhere in the Brillouin zone. Right? You can just to represent this as something that looks like a phase diagram. We plotted this. So basically here, this would be the area, and the blue curve is the area of these loops for this example as a function of the magnetic field. And then on the other side here in red, we have the minimum spin splitting in the Brillouin zone. So this would be like the altermagnetic-like phase, where you get a vanishing spin splitting. But then in this case, you get a ferromagnetic-like band structure, where the Fermi surfaces are completely disconnected, right? And I just want to emphasize that this depends a lot on the direction of the magnetic field. So these are for these special directions in which you preserve the mirror symmetries. If you take some other arbitrary direction of the field, say a field that lies in the xy plane, then it's not perpendicular to any mirror planes. For that case, immediately as soon as you turn on the magnetic field, you basically remove this altermagnetic-like behavior. You split the two Fermi surfaces, right? And here I was focusing on the effects of the Zeeman term, but as Jörg already mentioned, you can also get very similar physics if you apply strain, because symmetry here allows for a coupling between the magnetic field, the strain, and the altermagnetic order parameter. In this case, in the example, I was thinking about a magnetic field along the z direction, but applying the xy component of strain will have very similar effects for both some critical strain. You can also get this kind of transition. And finally, let me just give you 1 second example, which I find kind of amusing, just to say that that's not everything that happens in all the cases that we have tried to understand. If you take, for example, this example in the hexagonal symmetry B1G minus, the Hamiltonian looks like this. And then in this case, there is only one nodal line in the period 1 zone to begin with, in the absence of the magnetic field. That's the one that runs along the KZ axis. And then it's different from the case that I mentioned before, because if you look at the dependence for small kx and ky, you actually get this quadratic momentum dependence, a d-wave-like dependence around the kz axis. If you want to talk in terms of Berry phases, in this case it corresponds to 2 pi Berry phase, which is very analogous to quadratic band touches in two-dimensional semimetals, and which kind of tells you already that this kind of the line is doubled in some sense. And then we analyze what happens in this case when you turn on the magnetic field. And then there are actually 2 possibilities. The important point here is actually the topological invariant we have to look at is the one associated with the difference of the mirror eigenvalues across this nodal line. And in this case, it's actually trivial, because you have the same eigenvalues on both sides, which means that this line is not protected. It has to change somehow when you turn on the magnetic field. There are 2 possibilities here, depending actually on the sign of the magnetic field, which is the relative direction, depending on the sign of the altermagnetic order parameter. It's possible that you actually split into 2 lines. And then in this region between the lines, you actually get the opposite eigenvalue. Once that happens, now these lines are protected, and you can keep moving them until you get the transition at some finite critical field. The other possibility, also depending on the sign, is that actually the line is immediately gone, and you actually turn it into 2 Weyl points away from this mirror plane. And in that case, it's just get a Weyl semi-metal from this initial state. Okay, so and with that, I think I'm done. And thank you for your attention.
Thank you for being on time. We have 2 questions that I can see.
Thank you. Very nice talk. So in the real system, I mean, I have the experience that if you do not turn on the spin-orbit coupling, you should considering the spin group, right? Because you have this on-site symmetry that is time reversal symmetry act on the spin space. So from my realistic calculation experience, that you don't need this nodal line in this mirror plane. Am I right? So if you're working with the spin groups, yes,
right.
Yes, without spin-orbit coupling.
Without spin-orbit coupling, that's true.
Yes, so we don't need this nodal line that exactly within this mirror plane.
Before we turn the spin-orbit coupling in our case, we started with nodal planes with the collinear.
Yeah, but in 3D that we can have nodal line, but within this mirror plane, even though we have mirror plane in 3D.
But here, I mean, it's also it's not only a mirror plane; it's a nodal plane. I don't know if you're talking about the same. It means that the spin splitting actually vanishes on the entire plane.
Yeah, I'm question about what exactly the symmetry that protect your nodal line in the without turning on the spin-orbit coupling. I'm not saying this nodal plane, just nodal line.
There's no nodal line in that case.
But we see that in chromium.
That's different. You're talking about the thing with the same spin. It's the vio points that Jorn talked about that in 3D become lines. These nodal planes are the planes between that are coming from the altermagnetic order parameter. The ones that you're talking about in chromium-timonide, they're the equivalent of what he said when you have the same spin crossing that in 3D become nodal lines. They are not protected by anything. They may or may not be there.
But you have this on-side symmetry that is PT, but the T is in spin space. That you can have this eigenvalue that is minus 1 or plus 1 that can still protect this kind of nodal.
But then you probably have a non-symmetric symmetry.
No. It's just on-side symmetry.
I have a feeling that this is probably better solved in real time.
Yeah, thanks for the talk. I was confused about the statement when you flashed the tenfold way that you kind of consider only the non-crystallographic symmetries. But I mean, in the centrosymmetric altermagnets, the crystallographic symmetries change your codimension, right? Because you get a reality constraint, and this changes the codimension of your effective like KP 2 by 2. So that you end up in the right column of your tenfold way.
Yeah, well, what I can tell you for sure is that without any additional symmetries, all the Hamiltonians we looked at are trivial. So.
Yeah. Well, I mean, actually, that's another comment. The 0 only in the tenfold way only refers to a classification of certain type of matrices, but these can actually be non-trivial in terms of Stiefel-Whitney classes.
Okay.
Maybe that's an interesting
that we
thing to
didn't
look
look at.
at.
Yeah, so, okay, that'll be interesting.
So I have a specific example that I thought a little bit about it, and I wonder what you think about it. So we already discussed cobalt fluoride before. So if you apply, cobalt fluoride is collinear with spins along the z-axis. If you apply the strain in the xy plane, you get an induced magnetization also along the z-axis. So what you would expect is that the band structure should split at the gamma point. And does that mean that then you get nodal lines? And if that's the case, we already discussed that can in principle occur without spin-orbit coupling.
Yeah, I'm not very familiar with that
Well, it's a
material.
classic wave altermagnet in the absence of strain, but if you apply strain, you get a magnetization because it's it's piezo-magnetic.
Okay.
And if you apply the strain in the xy plane, the magnetic moment is along the z-axis, so it's parallel to the staggered magnetization. In that case, based on your analysis, I would expect these hyperbolic.
Yes, so you would you would
And
preserve
that's
nodal
that can
lines.
also
Yes.
occur in the absence of spin-orbit, because that's already been discussed.
Do we have any more questions?
If you don't have spin-orbit coupling, you have nodal planes. And Thomas is here; he can ensure that, right? The point of the spin-orbit coupling is that it lowers the nodal planes to nodal lines. That's the point we're trying to make. So
No longer the planes. Before you had nodal planes like this, right?
So it's the if you want to look at the material, right? You start with nodal planes. You can do in whichever order you want. We turn spin-orbit coupling first, becomes lines.
No spin-orbit coupling here.
I think cobalt difluoride has spin-orbit coupling.
No, I know, but that's
Right?
not,
So-
that's not the point.
No, that's fine.
Just shift the bands.
You,
Yeah, I think maybe the confusion, but the resolution is that it's no longer an altermagnet.
Yeah.
Right? Because the two sublattices are an equivalent.
Sure. Our point is that depending on the key point is that when you have spin-orbit coupling, you endow some of these lines. You can have accidental nodes. That's fine. That exists. We can see that every time. They are not protected by any symmetry. The point that we're trying to make is that once you have spin-orbit coupling, there are lines protected by two mirrors. So a perturbation that you apply, if they preserve a mirror, you don't get rid of these nodal lines. We're not trying to say there's no other nodal lines that one can possibly imagine. That's fine. But these are the ones that have a symmetry protection in the presence of spin-orbit coupling. I think that's the point. We're not saying that. Yeah.
Yeah, just to.
Yeah.
Just a comment on that. There was one case where they were considered with spin-orbit coupling with a higher dimensional symmetry that has nodal planes, even with spin-orbit coupling. Yeah, in the cubic one. And in that case, you apply the perturbation, the magnetic field, or strain in the xy plane, the nodal plane is gone. It becomes a line. So it seems that the planes are not protected, but the lines can have this sort of topological protection.
Just a small comment on planes. Sometimes we stick a little more to the name of surfaces. Not all surfaces, because some of them are not planes. Just to be clear. If there's no more questions, I think Rodrigo again.